I saw an article from this person. It says Joel Gruss. He has this really awesome article. I definitely recommend checking that out. But when I saw it, I was cracking up. It was hilarious. What we're going to be doing is we're going to be tackling FizzBuzz with neural networks. Why is that necessary? It's not necessary. It's just for fun, but it's like taking a bazooka to a fly, basically. And it's kind of hilarious to see this very simple problem get destroyed by neural networks. So let's have some fun, and I'm going to first showcase this FizzBuzz problem. This is standard. If you are not familiar with it by now, definitely check it out. But I'm going to run this to kind of show you the main functionality. It takes a number. If it's divisible by 3, it says it returns fizz. If it's divisible by 5, it returns buzz. If it's divisible by both, it returns FizzBuzz. Anything else, it just returns the input number as is. So this is effectively what we will want our neural network to be able to do. So the aim here is, yes, it is going to be overly complicated, but that's kind of the fun of it. What we're going to do is we're going to replicate our original FizzBuzz function, but we're going to be using a neural network that will serve basically like a black box, where there is some input, there's a desired output, but whatever goes on in the middle is kind of like unknown, because that's how neural networks work. I have here NumPy, Matplotlib, and some Keras. TensorFlow Keras is now the thing as well, so make sure to have those installed. By the way, I have a Jupyter Notebook here if you're not familiar with this. There's some instructions on my channel, but you can probably find some more online with how to install that kind of thing. So definitely feel free to work in that environment, or there is Kaggle. They have notebooks on Kaggle as well that do similar things. There's also Google Colab if you're familiar with that as well. Anyway, so we need to generate our data. The neural network requires a lot of data. So let's start off very simply with 1,000,000 data points. Here I'm creating a data frame, and is a million. If your computer can't handle as much, definitely feel free to lower that number. Here I'm creating a column called numbers, which is just the raw number. That is effectively our input. And then I'm going to take those numbers and map using the FizzBuzz function from before. I'm basically just reusing it to kind of get the proper correct answer. And I'm calling that FizzBuzz numbers as its own column. So if we run that and we check out the first few, we see kind of like what that looks like. This is just a data frame, a bunch of columns and rows basically. We're encountering a problem already. Neural networks and many models will require a number as the actual output. It could be one of two things: a continuous number or a categorical, like a discrete category. And right now, I think the most logical thing to do is definitely to go with the categorical target. So what we'll need to do is we're going to need to convert this column here, the FizzBuzz numbers, into a categorical representation of the same thing. And so what we'll do here is we'll take the numbers that represent the original number as 0. 1 represents fizz, 2 is buzz, and 3 is FizzBuzz. And so I'll need to convert that column. And so I have a little helper function here that does that. And here I'm taking those numbers, and again, I'm the FizzBuzz numbers, and I'm mapping it to that convert function and calling it a new column called target. So if we check out our data frame now, we see that we have our target. The target is not the only thing that needs to be considered. For a neural network, the input also matters a lot. If we fed in a single number, that's like one node effectively, there's not a whole lot of space for a neural network to find like the relationships within that input. And so there are a few ways that you can break a number down, but I think a very quick and easy way is just to take the binary representation of that number and use that as like individual inputs. So we're going to take a number, take the input number, break it down into binary, and that will be like a 1 or a 0 for a bunch of different nodes that are at the input. What this allows our neural network to do is to actually find the mathematical relationship within numbers, which in this case actually makes a lot of sense because we're dealing with numbers that are like divisible by 3 or divisible by 5. And so it makes a lot of sense to break down the numbers into that kind of way. So here I have a helper function called binary encode. So it looks complicated, but effectively it will output an array that is the binary representation of the input number. So for example, I have here the number 10, and I want to break that down into binary. So if I did that, it will look like this. This is the binary form, but broken down into like an array of individual numbers, which will be effectively the input one at a time into the neural network. And we see here what that looks like, 0, 1, 0, 1, 0. I have the breakdown here in math. I have a secondary parameter here as well, which represents the length of the array. The thing to realize is that because you're dealing with binary numbers, each spot can only house so much information. And so if you have a length of 5, for example, then you can actually see what's the largest number that that space can represent. So you can take 2 to the square root of that number, and then you minus 1 off of it. So given a length of 5 for a binary number, the largest number you can have that is represented in that space is up to 31. So we can also look at the math on that and say 2 to the 20th power minus 1. What does that look like? That has enough space for a million, a little more than a million actually. So there's enough space in just 20 digits. So that's what we'll be using. Okay, so let's prep our model. We'll be converting our inputs into a binary form, and then feeding that into the neural network, training it on lots and lots of data, and then we'll eventually build a model that is able to handle the input and get the target that we're looking for. So here I have the number of binary digits set to 20, like we mentioned before. I'm going to define capital X to be our array of input numbers. And so here I'm creating an array, and I'm doing like a list comprehension here where I'm taking the numbers, like the original numbers, which is 1 to a million, and just using our binary encode to encode each number, and that will be our X. And I'm also going to be taking our Y and using a function in Keras called toCategorical. This is needed for Keras specifically and their implementation. So we had a categorical column 0, 1, 2, 3, but that actually needs to be represented in another way just for Keras. So this is more of a Keras specific thing. And so I just want to kind of show you what that looks like. So if I run that, and we can see what our target looks like now, and we can see what it basically is doing is it's taking each target number and just representing it as like an array with the highest number being the index. It's just like it's associated with the index. So for example, this first value here is a 0 because the largest number, which is a 1, is in the 0th position. So I'm just showing you that it coincides with the target numbers as well. So 0, 0, 1, 0, 0, and this is the 1 index here. And you see the last number here is a 3. So that's what we see here is a 3. And what's interesting is that we can actually always convert from this format here back down to this by looking at the max argument within each individual array here. So that's what we'll actually be doing later when we get the output from our neural network. We're going to be just taking the max arg from each one of these. All right, so we're almost ready to start training our neural network. Before we go any further, we absolutely want to set aside some data to test whether or not the neural network is actually working. It's like a validation set, basically. And it's important to not include that data in the training because the only way to really validate to know that your model is working is for it to work on unseen data. I'll be setting aside the first 100 for testing, and the rest is basically going to be used for the training. Let's run that. And here's to showcase what the training set looks like. This is the training input. Remember that the input is the binary representation of the numbers. The training target is also in line. Whatever we do with the input, we have to also kind of split the target as well because the input needs to be associated with the target. So now we can go into the modeling part. So I'm going to be building a very simple neural network. Simple, relatively speaking, because the problem is actually not very hard to solve for a neural network. So what I'll be doing is taking the input shape, which if you remember is 20 long, 20 represented as the length of the binary values, which is 20 individual elements. So we're going to just dump in an array of 20, and that's going to be associated with 20 inputs. What we'll do is we'll have those 20 inputs get connected with 128 nodes in the first hidden layer, and another layer of 64 nodes in the second hidden layer. This is actually where the magic happens in a neural network. This is where the quote unquote learning is happening, where the neural network is actually learning the relationships between the things that are in the input. And then we have to make sure to have an output layer. In this case, it's going to have 4 output nodes, 4 referring to the 4 distinct categories that we're looking for. So eventually we're going to have, for each input, there will be an array of 4, which represents the likelihood of the category, basically. And so when we do the argmax, we're looking for out of those 4 categories that have like a probability, we're looking for the one that's the max argument, which is associated with the index. The index is our category. All right, so let's build our model. And we're going to have to tell the model how it's going to properly assess the training process. And so what I'll want to use is categorical cross entropy as our loss. I'm going to be also using the atom optimizer, which is something that's used during the gradient descent process. More complicated than I can have time to get into right now. But if you have any questions, by the way, definitely leave some questions in the comments. I would be more than happy to give any clarity on that. So let's run that. I don't want the process to go on forever. If we see the score not change or the loss not change after 3 epochs, then we can say we're done. We don't want to keep going. So this is what's called early stopping. And that's all. It's just a nice parameter to have so that you're not stuck there forever waiting for your model to fit. An epoch, by the way, is basically running through your entire training data once. And we're going to start this process with 20 epochs, so not too much. But here is where we actually start training our model. This is called the fitting process. And so what we'll do is we're putting in our training data, both the input and the output. And we also have a validation set, which is only used for checking to see how good the model is, but it is not used in the training process in terms of like actually changing anything about the model. We're setting, again, 20 epochs, a batch size of 128. This is just how many values are going to be used to train before backpropagation happens. So it's a nice parameter to check out. And then our callback is the early stopping. So let's run this and see what happens. Okay, so we're starting the fitting process. We see that our model accuracy is about 50% right now, a little over. But as we continue the training process after epochs 2, 3, 10, that number should be going up. And so what you see is going on here, even during the second iteration, the second epoch, we see that our loss is going down, which is preferable. Loss is something you want to reduce, and accuracy is going up. If we're looking for accuracy, that's a good metric in our categorical case. Then we want accuracy to go up to 100% or 1. So it's looking good, and we're already on the 4th epoch, and our accuracy is already almost up to 99-100-ish%. I did not know it would go all the way to 20 epochs, but whatever. We see that it has a final training accuracy of close to 100%, and it definitely has an accuracy on the testing set for 100% here. So let's check out some of the graphs that I like to use here. This is just plotting out the loss by epoch. Okay, so we see here that the training loss and the validation loss are both going down, and they're basically teetering at 0 here. So we definitely ran it, I think, as long as it needs to be. And we see that the validation loss is dropping actually a little quicker than the training loss, which is a little unusual, but not that weird. All right, so let's look at the accuracy, which we want basically the opposite effect. We want to see it get larger and approach 100%. And that's exactly what we see here. Again, the training set is a little early in terms of like it approaching 100%. After about epoch 6 or 7, we see that the training accuracy also kind of approaches 100% as well. So that is looking pretty good. I'm pretty confident that this model will be able to replicate the FizzBuzz functionality. So let's put in and use our model to predict and give output for the testing set. So we're feeding in the testing set, and that's the first 100 numbers. So we want to get out the predictions from that, and let's see what that looks like. Okay, so that looks like a hot mess, but keep in mind that what we're seeing here is the probability for each category. And so this first output here is an array of length 4, which represents the likelihood for each category by index. So index 0 has basically 100%, and everything else has like 0% here. So there's high confidence that it's actually the category 0. And so what we want to do here is take the argmax of each position and then look at the index, and that's what we're looking for. So what I have here is a simple np.argmax. I'm popping in the predictions to get that exactly. So let's see what that looks like. All right, we see the 0, 0, 1. So these are actually the categorical representations that we were looking for. And we'll look to see, this is just the first 10, but I want to look at just the true values now. So this is what our model is outputting. That's what our model is predicting. Let's see what the actual true values look like. And we can see that the true values match up basically 1 for 1, but that's not everything. Let's make sure that we're looking at all the outputs. And what I have here is the scoring function for accuracy, and I'm going to put in the first 100 values, the true target, and then the predictions that we saw. And we see that we get an accuracy of 100%. So right now, if we're looking at the numbers between 1 and 100, our model is perfectly predicting what the actual truth is supposed to be. So it's outputting what we want effectively. So we can say that we're done here. If we wanted to, we can actually go back and kind of convert the output to the form that we're looking for, which is the FizzBuzz output. And so here I have a simple function that does exactly that. So let me run that. And here I'm just going to do a list comprehension that takes in the output and gives you the expected final. And that's what we see here. All right, so was that overkill? Absolutely. Was it fun? Absolutely as well. I loved this exercise. It was very fun to like go through this process. Also just like tweaking things to work for the neural network. I think actually I learned a lot, to be honest, about how neural networks work in the sense of whatever the input is, it needs to have enough space to kind of like work with it. You don't just feed it a number, and it has to work with these hidden layers in such a way that it's actually learning. So I actually tried this problem out with just one hidden layer, and it actually didn't do so well. So it kind of taught me that even though it seems like a simple problem, for a computer to understand that relationship inherently actually is a little bit more complicated than I gave it credit for. Anyway, folks, if this is the kind of content you like, make sure to like, subscribe, and do all the good things. And I will see you next time. Have a good one.